Hello and welcome to the Maths 2 component of the online BSc degree on data science. In today's video, we are going to look at Cramer's rule, which employs the determinant in order to find the solutions of a system of linear equations when the coefficient matrix is invertible. Let's go on and do an example. So, let's look at this linear system. So, 4x1 minus 3x2 is 11 and 6x1 plus 5x2 is 7. So, let us recall what was the matrix representation. So, that is Ax is B. So, the matrix A is given by the coefficients. So, 4 minus 3, 6, 5 and B is the constants on the right. So, it is a column vector or column matrix 11, 7. And x is the unknowns x1, x2. So, this it is easy to compute this solution. It has a unique solution, x1 is 2 and x2 is minus 1. Let us quickly go through how. So, we can multiply the first one by 3 to get 12x1 minus 9x2 is 33. We can multiply the second one by 2 to get 12x1 plus 10x2 is 14, and then we subtract, let us say, the first one from the second one. So, in that case we get 19x2 is so what should we get? So, 14 minus 33, so that is minus 19. So, that tells us x2 is minus 1, and then we can substitute it in one of these expressions and get that x1 is 2, one of these equations, and get that x1 is 2. Okay. So, we can easily check that this is the unique solution. So, now let us do something slightly different and reinterpret this using determinants. So, here is the same example and here is how we will apply Cramer's rule. So, we look at the coefficient matrix A. So, that was 4 minus 3, 6 and 5. Let us compute the determinant of A. So, if we do that, that is 4 times 5 minus negative 3 times 6. So, that is 20 plus 18, which is 38. Let us keep that value in mind. So, the determinant of A is 38. So, replace the first column of A by the column vector B, and we will call that matrix A subscript x1, because the first column are the coefficients corresponding to x1 in the two equations. So, A subscript x1 is 11 minus 3, 7, 5. So, we have replaced the 4, 6 over here by 11, 7. Okay. Replace the second column of A by the column vector B and call it x2, A x2. So, A subscript x2. So, we are doing the same thing for the second column. So, now the first column is the same as the first column of A, and the second column is replaced by 11, 7. So, we get 4, 11, 6, 7, that is A subscript x2. Let us calculate determinant of A x1. So, you can do this. This is 11 times 5 minus negative 3 times 7. So, that works out to 76. And then let us calculate the determinant of x2, sorry, A x2, A subscript x2. So, if you do that, that is 4 times 7 minus 11 times 6, that is minus 38. So, remember that the determinant of A was calculated to be 38. So, let us keep this in mind, 38, 76 and minus 38. Okay. So, now what do we do? So, Cramer's rule will say, let us calculate determinant of A subscript x1 by determinant of A, and determinant of A subscript x2 by determinant of A. So, let us do that. So, this is 76 by 38, and this is minus 38 by 38, and these are exactly the solutions. So, x 1 is 2, remember that is what we got in the first slide, and x 2 is minus 1, which is exactly what this is. Okay. So, at least in this example we have this strange method using determinants, and it gives us the solutions that we require, that we should have got, not required. Okay. So, let us study what is Cramer's rule in general. So, this is for when the coefficient matrix is an invertible matrix. Fine. So, what do we mean by invertible? Invertible means that the inverse exists. Okay. So, consider the following system of linear equations of two variables. A11 x1 plus A12 x2 is B1, A21 x1 plus A22 x2 is B2. So, the matrix representation here is A is A11, A12, A21, A22, and B is B1, the column vector B, B1, B2, and the assumption here is that the matrix A is invertible, meaning its inverse exists, and because its inverse exists, remember that in a previous video with determinants we have seen that determinant of A inverse is 1 by determinant of A, which in particular means that determinant of A is non-zero. Okay. So, 1 by determinant of A exists. Okay. So, let us define these two matrices as in the previous example. So, we replace the first column by the vector B1, B2, and we call that new matrix A subscript x1, and we replace the second column by the column vector B, and we call that new matrix A subscript x2. Okay. And then Cramer's rule says the solution of the system of equations, and I am saying D, which means it is a unique solution in two variables. So, this is determinant of A subscript x1 by determinant of A. Note that this division makes sense because it is invertible, and x2 is determinant of A subscript x2 by determinant of A, again makes sense, and we know explicitly what these expressions are. For 2 by 2 matrices the determinant is easy to compute. So, this is the numerator for the first expression is B1 A22 minus A12 B2, and the numerator for the second expression is A11 B2 minus B1 A21, and the determinant of the matrix A is A11 A22 minus A21 A12. Fine. So, that is the algorithm you have to follow for Cramer's rule to find the solutions of a system of equations where the coefficient matrix A has non-zero determinant. Okay, we can make this more general. So, let us do a 3 by 3 see Cramer's rule for 3 by 3 matrices. So, again here the coefficient matrix must be invertible. So, the determinant of A must be non-zero because we divide by that determinant. So, here is the system of linear equations in 3 variables. So, recall that its matrix representation is Ax is B, where A is the coefficient matrix and B is this column vector of constants B1, B2, B3. Okay. So, in that case what is Cramer's rule? So, we will have to define these new matrices, again 3 by 3 matrices. So, A subscript x1 is where you replace the first column of A by the column vector B. A subscript x2 is where you replace the second column vector, the second column of A by B, and A subscript x3 is where you replace the third column vector, third column of A by B. Okay, and then how do we get the solution? So, the solution, meaning again it is unique, of the system of equations that we saw is x1 is determinant of A subscript x1 by determinant of A, x2 is determinant of A subscript x2 by determinant of A, and x3 is determinant of A subscript x3 by determinant of A. Again, very important is that the determinant here must be non-zero, otherwise of course we can't divide, and assuming that A has an inverse ensures this, or explicitly we can say that determinant of A is non-zero. So, how did we define these A subscript x1, A subscript x2, A subscript x3? So, in the first one the first column was replaced, in the second one the second column was replaced, and in the third one the third column was replaced. So, these and the notations should tell you which columns are replaced, because x1 means the coefficients corresponding to x1, that is the column which is replaced. So, those were A11, A21 and A31, and similarly for x2 and x3. Okay, so, this is Cramer's rule for 3 by 3 matrices, or for a system of linear equations in 3 variables. Fine, maybe let us do a quick example. So, consider this system of equations where the coefficient matrix. So, I am, instead of writing down the system, I am writing down the coefficient matrix and the constants. So, the coefficient matrix is 1 0 3 0 2 5 4 3 1, and the constants are 0, 2 and 1 respectively for the 3 equations. So, to use Cramer's rule, first let us look at the determinant. So, the determinant of A, so we will have to compute this. So, the determinant is minus 37. So, I will encourage you to compute this. So, since it is non-zero, we can apply Cramer's rule. So, let us follow the next steps in the procedure for Cramer's rule. So, we have to compute these matrices A subscript x1, A subscript x2 and A subscript x3. So, how do we compute these matrices? We replace the corresponding columns by the column B. So, here we get 0 to 1. So, B, this is B and the other things remain same. Here we get 0 to 1 in the second, in place of the second column, and here we get 0 to 1 in place of the third column. Okay, so, these are our matrices A subscript x1, A subscript x2 and A subscript x3, and then we compute their determinants. So, the determinant of A subscript x1 is 12, you can check this. So, here we have first row has 2 zeros. So, this is an easy computation. Similarly, for A subscript x2, you can check this is minus 27, and A subscript x3 the determinant is minus 4. And then by Cramer's rule we get that the solution to this system of equations is x1 is minus 12 by 37, x2 is 27 by 37 and x3 is 4 by 37. Okay. So, I will encourage you to substitute these x1, x2, x3 and check that indeed this is the solution, and you can do a usual method of solving equations and check that indeed this is the solution. Okay. So, finally, let us end with Cramer's rule for the n by n case. So, now if you have n systems in a system of n linear equations in n unknowns. So, remember here that we should have the coefficient matrix has to be square first of all. So, we need n equations in n unknowns, yeah, this will not work otherwise. And the second thing we need here is that the coefficient matrix is invertible, or that the determinant is non-zero. Okay. So, this is the general system of equations. A is this matrix of coefficients A I j, A11, A12, etc., and then B is the constant. So, column vector with B1, B2, Bn. Then you define AXI, that is A subscript xi. This is a new n by n matrix, and how do we obtain this? We obtain this by, for the ith column you substitute you replace it by the column vector B. Okay. So, if you do that, then you compute its determinant, and then the solution to this system of linear equations. So, Cramer's rule states that it is given by xi is determinant of a subscript xi by determinant of a, right. So, we compute for each I. So, x1 is determinant of a subscript x1 by determinant of a, x2 is determinant of a subscript x2 by determinant of a, and so on up till xn is determinant of a subscript xn by determinant of a. That is what Cramer's rule states. In Cramer's rule, remember that we need, this is very important, n equations in n unknowns. Yeah, that is when we can apply it, and further we need that the determinant of the coefficient matrix A is non-zero, okay, and then we can explicitly work out what the solution is. Thank you.